Before we begin, find yourself somewhere comfortable. This is a story told at the pace of starlight, meant for those quiet hours when the mind is ready to wander and wonder. If you drift along the way, that's perfectly all right. The sun has been there for billions of years. It will wait. Right now, as you listen to these words, something is happening on the surface of our sun. Dark regions the size of Earth itself are rotating into view, drifting slowly across that familiar disk of light we've known since childhood. Some of them are 10 times larger than our entire planet. They appear as shadows against the blinding brilliance of our star, cool patches in an ocean of fire, and they have been appearing there, vanishing, reappearing, for as long as humans have looked upward and wondered. We call them sunspots. The name is simple, almost quaint, like calling the Grand Canyon a ditch or the ocean a puddle. But perhaps that simplicity is fitting. For thousands of years, people have seen these marks and tried to understand what they meant, tried to fit them into stories about the heavens and the earth, and the relationship between the two. Ancient Chinese astronomers recorded dark marks on the sun as early as 800 years before the Common Era. They watched the sky with a patience we can barely imagine now, in our age of instant answers and constant stimulation. Night after night, year after year, generation after generation, they observed and recorded and passed their knowledge forward through time. They believed these marks were omens, signs from heaven that something significant was about to occur. And in a way, though they could not have understood it as we do now, they were not wrong. Sunspots do signal something significant. They mark regions of intense magnetic activity, places where the sun's invisible forces twist and build and sometimes explosively release. The sun appears unchanging to us. It's a yellow disk hanging in the sky, constant and reliable. We wake to its light. We set our rhythms by its movements. We take for granted that it will rise tomorrow exactly as it rose today, that it has always been this way and always will be. But the sun is not constant. Beneath that familiar glow lies a churning ball of superheated plasma, a nuclear furnace burning through 400 million tons of hydrogen every single second. And on its surface, where temperatures reach 5,500 degrees Celsius, there are storms that make the worst hurricanes on Earth look like a gentle breeze. The modern scientific study of sunspots began in the early 1600s, when Galileo Galilei turned his newly invented telescope toward the sun and saw something that contradicted the religious teachings of his time. The heavens were supposed to be perfect, unchanging, eternal. But there on the face of the sun were dark blemishes that appeared, changed, and disappeared over the course of days and weeks. The sun, like everything else in nature, was dynamic and imperfect. It's difficult now to imagine how revolutionary this observation was, how much it challenged the certainty that the sky was separate from the earth, pure while we were flawed, constant while we were temporary. What Galileo could not have known is that these dark spots are actually cooler regions on the solar surface. While the surrounding photosphere blazes at nearly 10,000 degrees Fahrenheit, the centre of a sunspot, the dark region called the umbra, may be only 6,300 degrees. This temperature difference is what makes them appear dark against the brilliant background. They are not truly dark at all. If you could somehow isolate a sunspot and view it against the blackness of space, it would glow with blinding intensity. It only appears dark because it is surrounded by even brighter material, like a candle flame that seems dim when held up to the sun. But why are sunspots cooler? The answer lies in magnetism, in forces we cannot see, but which shape everything around us. Deep within the sun, in the churning convective zone where plasma rises and falls like water boiling in a pot, the rotation of our star twists and tangles its magnetic field lines. These field lines become concentrated in certain areas, bundled together like cables, and when they break through the surface, they inhibit the normal convection of heat from the interior. Think of it like placing a dam in a river. The magnetic field lines block the upward flow of heat, creating a region that is cooler than its surroundings. The magnetic field strength within a sunspot is extraordinary. Earth's magnetic field, the invisible shield that protects us and guides, compasses and allows migrating birds to find their way across continents, measures approximately half a Gauss at the surface. Sunspots can have field strengths of 2,000 to 5,000 Gauss. This is thousands of times stronger than anything we experience on our planet. Concentrated in areas that could swallow Earth whole, sunspots rarely appear alone. They typically form in pairs or groups, with each spot in a pair having opposite magnetic polarity. One spot acts like a magnetic north pole, the other like a south. Magnetic field lines arc between them, rising high into the solar atmosphere before looping back down, and when these field lines become too twisted, when they cross and reconnect in new configurations, enormous amounts of energy can be released in an instant. This is how solar flares are born, how the sun reaches across 93 million miles of empty space and touches us. The number of sunspots on the sun is not constant. It follows a cycle that astronomers have tracked for nearly 300 years, a rhythm as regular and mysterious as the turning of seasons. During what we call solar minimum, the sun may go days or even weeks without a single visible sunspot. The solar disk appears clean and quiet, almost featureless. But during solar maximum, dozens or even hundreds of spots can pepper the surface at any given time, and it is during solar maximum that the risk of dangerous solar storms reaches its peak. We are currently in solar cycle 25. The cycle began in December of 2019, when the previous cycle reached its minimum and the sun grew quiet. Scientists predicted it would be a relatively weak cycle, similar to the one before, with activity peaking sometime in 2025. But the sun, as it often does, had other plans. Solar cycle 25 has exceeded every prediction, ramping up faster than expected, producing more sunspots than forecast, unleashing powerful storms that lit up skies around the world with colours that people in southern latitudes had never seen before and might never see again. When you look up at the sun, if you look up at it tomorrow morning or any morning, remember that you are looking at something both familiar and strange. You're looking at the same star that ancient Chinese astronomers watched, that Galileo studied, that has been the constant backdrop to every human story ever told. But you're also looking at a nuclear reactor 400,000 times more massive than Earth, its surface covered in dark magnetic storms, any one of which could spawn events powerful enough to disrupt everything we take for granted. The dark spots on our star are not new. They have been there all along, appearing and vanishing in their 11-year rhythm, sometimes violent, sometimes quiet, entirely indifferent to the civilization we have built beneath their light. But now, for the first time in human history, we're paying attention, we're watching, we're beginning to understand. And what we have learned is both reassuring and unsettling, because the dark spots are not just marks on the sun, they're doorways to something greater, windows into forces that shape the solar system and continue to shape it still. And sometimes, rarely but inevitably, those forces reach out and remind us how small we are, how fragile our electric world has become, how much we depend on the continued good behaviour of a star that owes us nothing and promises nothing. In 1859, on a clear September morning, a quiet English astronomer looked through his telescope and saw something no human had ever recorded before. What happened next would change our understanding of the sun forever and prove that our star, for all its constancy, is capable of violence we're only beginning to comprehend. The morning of September 1st, 1859, was clear and bright over the town of Redhill in Surrey, England. Richard Christopher Carrington climbed into his private observatory, a small structure attached to his country estate, and prepared for another day of solar observation. He'd been studying the sun for years, meticulously recording the positions and movements of sunspots, trying to understand the patterns that governed their appearance and disappearance. It was patient work, the kind of work that requires a temperament suited to watching things that change slowly, almost imperceptibly, day after day. Carrington was not a professional astronomer. He was a brewer by trade, having inherited his family's business. But his true passion lay in the heavens, and he had built one of the finest private observatories in England. His telescope was equipped with filters and projection screens that allowed him to safely observe the sun without destroying his eyesight. And day after day, he would sketch the dark spots on the solar disk, noting their positions, their shapes, the way they evolved and transformed over time. On this particular morning, Carrington noticed an unusually large and complex group of sunspots near the centre of the solar disk. He began to sketch them, carefully noting the darker, umbral regions and the lighter penumbral areas surrounding them. It was routine work, the kind of observation he had made hundreds of times before. And then, at approximately 11:18 in the morning, something extraordinary happened. 2 patches of intensely bright white light suddenly appeared within the sunspot group. Carrington later described them as kidney-shaped, blazing with a brilliance that far exceeded the already blinding solar surface. He stared in amazement, uncertain what he was seeing. Nothing like this had ever been recorded. Nothing like this was supposed to be possible. The bright patches moved, drifting across the face of the sunspot group over the course of about 5 minutes. Then, as suddenly as they had appeared, they began to fade. Within moments, they were gone entirely, leaving the sunspot group looking exactly as it had before. What Carrington did not know, could not have known, is that he had just observed the first recorded solar flare in human history. That brilliant flash of white light was the visible signature of an enormous magnetic explosion on the sun's surface, and the consequences of that explosion were already racing toward Earth at nearly 1 million miles per hour, crossing the vast emptiness of space, aimed directly at our planet like an arrow loosed from a bow. Approximately 18 hours later, the world began to change. On the night of September 1st and into the early hours of September 2nd, auroras appeared across the entire planet. These were not the gentle northern lights familiar to residents of Alaska and Scandinavia. These were apocalyptic displays of colour that reached down to the tropics. People in Cuba looked up and saw crimson curtains dancing across the sky. Observers in Panama witnessed green and red lights that seemed to set the heavens on fire. In Japan, in Australia, in Chile, people who had never seen an aurora in their lives stepped outside and stared in wonder and terror at skies that had transformed into something alien and beautiful. In the Rocky Mountains of North America, gold miners woke in the middle of the night, convinced that dawn had arrived. The auroral glow was so bright that they began preparing breakfast at 1 o'clock in the morning, only to realize hours later that the sun had not yet risen. In the northeastern United States, people reported being able to read newspapers by the light of the aurora alone. The sky itself had become a lantern, casting shadows, illuminating the world in colors that belonged to dreams or visions, not to the ordinary night. But the beauty of the lights masked a more sinister reality. Around the world, the telegraph system, the high technology of the Victorian era, began to fail. The telegraph was the internet of the 1850s. It was the first technology that allowed instantaneous communication across vast distances. Messages that once took weeks to deliver by ship or horseback could now be sent in minutes. Financial markets depended on it. Governments depended on it. The world was becoming connected in ways that had never been possible before. And on the night of September 1st, 1859, that connection shattered. Telegraph operators reported sparks flying from their equipment. Some received severe electric shocks when they touched their machines. In several stations, the telegraph paper caught fire, set ablaze by mysterious currents flowing through the wires. The excess electrical energy in the atmosphere was inducing powerful currents in the long metal lines that crisscrossed the continents. In some cases, operators discovered that they could send and receive messages even with their batteries disconnected. The storm itself was providing enough electrical power to operate the telegraph. It was a terrifying demonstration of the energy that had been released by that brief flash of light Carrington had observed. The disruption lasted for days. Telegraph communication across Europe and North America was severely impaired. Some lines were damaged and required repair. Others simply refused to work properly until the storm subsided. The world's first global communication network had been temporarily crippled by a phenomenon that no one understood, and the questions that followed would take decades to answer. Carrington himself was cautious about drawing conclusions. He noted the coincidence between his observation of the solar flare and the subsequent geomagnetic disturbance, but he understood that correlation did not necessarily mean causation. "One swallow does not make a summer," he wrote. But over the following decades, as more observations accumulated, the connection became undeniable. The sun was capable of producing explosions of light and energy that could travel across 93 million miles of space and affect conditions on Earth. The Carrington event occurred in a world that was just beginning to electrify. Telegraph wires were the only significant conductors vulnerable to the currents induced by the storm. The damage was inconvenient but ultimately manageable. Within days, the system was restored. Life continued. But the warning had been delivered, even if few people recognized it as such. 130 years later, on March 13, 1989, the Sun delivered that warning again. In the early hours of that Monday morning, as most of Quebec slept, a powerful coronal mass ejection slammed into Earth's magnetic field. At 2:44 in the morning Eastern Time, the Hydro-Quebec power system began to fail. Transformers overheated, circuit breakers tripped. Protective relays designed to prevent damage began shutting down sections of the grid in a cascading sequence that moved faster than operators could respond. Within 90 seconds, the entire system collapsed. 6 million people woke to cold and darkness. The blackout lasted 9 hours. People found themselves trapped in elevators between floors. The Montreal metro shut down completely. Without electricity, heating systems failed, and in March, nighttime temperatures in Quebec can drop well below freezing. For 9 hours, one of the largest and most modern electrical systems in North America was completely non-functional, and the only reason it came back at all was that the storm eventually subsided and engineers worked through the day to restore power section by section. The Sun does not care about our calendars or our conveniences. It does not know that we have built a civilization utterly dependent on electricity and electronics. It simply follows its own rhythms, its 11-year heartbeat of activity and quiet. And sometimes, that heartbeat touches us in ways we're only beginning to understand. The flash of light that Carrington saw in 1859 was a message sent across space and time, a reminder that we live at the mercy of forces far greater than ourselves, forces that were ancient before we existed and will continue long after we are gone. There is something protecting you right now, something you cannot see or feel or touch, something that has been protecting every living thing on this planet for billions of years. It surrounds the Earth like an invisible cocoon, stretching tens of thousands of miles into space, deflecting particles and radiation that would otherwise strip away our atmosphere and sterilize the surface. We call it the magnetosphere, and it is the reason we are here at all. Deep within the Earth, nearly 3,000 miles below your feet, liquid iron churns and flows in the outer core. The temperature there exceeds the surface of the Sun, and the pressure is millions of times greater than what we experience at sea level. This molten metal, driven by the heat escaping from the planet's interior, moves in vast currents that generate electric currents, and those electric currents produce a magnetic field that extends far beyond the surface, far beyond the atmosphere, out into the darkness of space where it meets the solar wind. The solar wind is not really wind at all. It is a constant stream of charged particles flowing outward from the Sun at speeds of hundreds of miles per second, a river of electrons and protons that fills the solar system. When this river encounters Earth's magnetic field, something remarkable happens. The field deflects most of the particles around the planet, channeling them away like water flowing around a stone in a stream. Some particles become trapped in belts of radiation that encircle the Earth, held there by the magnetic field lines. Others are funneled toward the poles, where they collide with atoms in the upper atmosphere and create the auroras, those curtains of green and red and purple light that dance across polar skies. Without this shield, the solar wind would slowly erode our atmosphere. Over millions of years, the bombardment of particles would strip away the gases that make life possible, leaving behind a barren world like Mars. Mars once had a magnetic field, scientists believe, billions of years ago when its core was still molten and churning. But the core cooled and solidified, the magnetic field collapsed, and the solar wind began its patient work of erosion. Today, Mars has only a thin whisper of atmosphere remaining, and its surface is bathed in radiation that would be lethal to any life we know. Earth could have gone the same way. The processes that generate magnetic fields in planets are complex and fragile, a slightly different composition, a slightly different size, a slightly different thermal history, and we might have ended up like Mars, a world that lost its protection and paid the price. But we got lucky. The Earth's core remained molten, the magnetic field persisted, and life was able to flourish in the shelter it provided. The magnetosphere is not a perfect shield. During powerful solar storms, when coronal mass ejections strike the Earth, the magnetic field is compressed on the side facing the Sun and stretched into a long tail on the night side. the boundary between the magnetosphere and the solar wind called the magnetopause, can be pushed inward, sometimes to within a few thousand miles of the surface. Particles that would normally be deflected can penetrate deeper into the magnetic field, energizing the radiation belts and creating intense auroras at lower latitudes than usual. But even during these storms, even when the field is compressed and stressed and saturated with energy, it continues to protect us. The atmosphere below absorbs most of the X-rays and ultraviolet radiation from solar flares. The magnetic field deflects the bulk of the charged particles, and life continues, largely unaware of the invisible battle being fought in the space above. We did nothing to earn this protection. We did not build the magnetosphere or maintain it or pay for it. It was here long before the first humans looked up at the sky and wondered what the lights were, long before our ancestors climbed down from the trees, long before life crawled out of the oceans onto land. It is a gift of physics and geology, of iron and heat and rotation, a gift we receive every moment of every day without thought or gratitude. Think about that for a moment if you can. Think about the molten iron flowing beneath your feet, creating invisible lines of force that extend into space. Think about the charged particles from the sun, racing toward us at unimaginable speeds, only to be turned aside by fields we cannot see. Think about how fortunate we are to live on a planet that happened to have the right size, the right composition, the right thermal history to maintain this shield for billions of years. Other planets were not so fortunate. Venus, similar in size to Earth, rotates so slowly that it cannot generate a strong magnetic field. Mercury has only a weak field, barely sufficient to provide any protection. The gas giants have powerful magnetic fields, but they have no solid surface where life like ours could exist. Mars, as we have seen, lost its field long ago. In all the solar system, Earth alone combines a strong magnetic field with a solid surface, and an atmosphere thick enough to support complex life. We won the cosmic lottery simply by being born here. We did nothing to deserve it. We had no choice in the matter. But here we are, protected by forces we barely understand, living in the narrow band of conditions where life can not only exist but thrive. The magnetosphere changes constantly, responding to the solar wind, to the rotation of the Earth, to the variations in the sun's activity. It breathes and flexes and adjusts, a dynamic system that has been protecting this planet for more than 3 billion years, and it will continue to protect us as long as the core remains molten and the planet continues to turn, as long as the iron keeps flowing in the darkness beneath our feet. Sometimes, on clear nights far from city lights, you can see the evidence of this protection with your own eyes. The auroras that appear near the poles are the visible signature of the magnetosphere at work, particles channeled along magnetic field lines, colliding with atoms of oxygen and nitrogen, releasing energy as light. They are beautiful, those curtains of colour dancing across the sky. But they are also a reminder of what is being kept at bay, of the constant bombardment that would destroy us if not for the invisible shield that turns it aside. We live our lives unaware of this protection, just as we live unaware of gravity or air pressure or the countless other forces that make existence possible. But it is there nonetheless, working every moment, deflecting particles, absorbing radiation, maintaining the conditions that allow us to breathe and think and wonder about our place in the universe. And now, as the sun reaches its maximum of activity, as sunspots pepper its surface and flares erupt with increasing frequency, the magnetosphere is being tested once again, just as it has been tested countless times before throughout the long history of our planet. The sun has a heartbeat, not a pulse of blood through arteries, but a rhythm of magnetic activity that rises and falls over approximately 11 years. At the start of each cycle, the sun is quiet, almost serene. Few sunspots mark its surface. Solar flares are rare and typically weak. The corona, that outer atmosphere visible during eclipses as a pearly halo around the dark disk of the moon, appears calm and stable. Then, gradually like a sleeper stirring toward wakefulness, activity begins to build. Sunspots appear at higher latitudes on the sun's surface and slowly drift toward the equator as the cycle progresses. The magnetic field becomes more complex, more twisted, more prone to the kind of violent release we now recognize as solar flares and coronal mass ejections. the Sun enters its restless phase, and the space between our star and our planet becomes filled with energy and particles racing outward into the darkness. At solar maximum, the peak of this 11-year cycle, the Sun reaches its greatest activity. Sunspots pepper the surface in numbers not seen during quieter years. Powerful flares erupt regularly, sometimes multiple times per day. The risk of severe space weather events affecting Earth climbs to its highest point, and then, just as gradually as it began, the activity starts to decline. The cycle winds down toward the next minimum, and the pattern repeats, as it has repeated for as long as the Sun has existed, as it will continue to repeat long after we're gone. Scientists have been tracking these cycles since 1755, when astronomers began systematically counting sunspots. We are currently in solar cycle 25, the 25th cycle since those regular observations began more than 2.5 centuries ago. And this cycle has surprised everyone who tried to predict its behaviour. When solar cycle 25 began in December of 2019, the scientific consensus was clear. The cycle would be weak to moderate, similar to the relatively quiet solar cycle 24 that had preceded it. Expert panels forecast a maximum of around 115 sunspots, occurring sometime in the middle of 2025. Some researchers even speculated that we might be entering a prolonged period of reduced solar activity, a grand minimum like those that have occurred in the past when the Sun grew unusually quiet for decades at a time. The Sun, as it often does, had other plans. From the very beginning, solar cycle 25 exceeded expectations. Activity ramped up faster than predicted. Sunspot numbers consistently ran higher than the forecast curves. By 2023, just 3 years into the cycle, it had already surpassed the previous cycle at the equivalent point. The predictions, careful and considered as they were, had underestimated what the Sun was capable of doing. In May of 2024, the Sun delivered a storm that forced the world to pay attention. A barrage of powerful solar flares and coronal mass ejections erupted from active regions on the Sun's surface over the course of several days. The coronal mass ejections arrived at Earth starting on May 10th, bunching up in waves, creating a geomagnetic storm that reached the highest level on the severity scale. It was the first storm of that intensity in over 20 years. The auroras that followed were spectacular beyond measure. People across the world looked up and saw colours dancing across skies that should have been dark. In North America, auroras were visible from states that almost never see them: Florida, Texas, Arizona, even the Florida Keys. Across Europe, the lights extended as far south as Portugal and Spain. In Africa, observers in Algeria witnessed the display. Throughout Asia, from Turkey to Japan to northern India, people photographed curtains of green and red and purple light where none should have been visible. By one estimate, these auroras may have been among the strongest in 500 years, visible at latitudes where they appear perhaps once or twice in a human lifetime. And yet, for all their beauty, they were also a warning. The same forces that created those magnificent lights also disrupted GPS signals, affected power grids, and reminded us once again how dependent we have become on technologies vulnerable to the Sun's moods. On October 15, 2024, space agencies made it official. The Sun had reached solar maximum. The announcement came with careful qualifications. This did not mean solar activity had peaked in any single month. The exact month of maximum sunspot numbers would not be identifiable for several more months after scientists could confirm a consistent decline. Solar cycles can experience double peaks, with activity rising and falling before rising again. The announcement simply confirmed what observers already knew. We were in the maximum phase, the period of greatest activity and greatest risk, and the Sun was not finished. November of 2025 brought more violent activity. Powerful flares erupted, causing radio blackouts across continents, hurling coronal mass ejections toward Earth. The northern lights appeared again across much of the northern hemisphere, visible in places where most people had never seen them before. Each storm was a reminder that solar maximum is not a single moment, but a prolonged period, a season of activity that can last for months or even years. December brought the largest sunspot region in a decade, a dark patch on the Sun's surface more than 10 times the width of Earth. Amateur astronomers with filtered telescopes captured images of the enormous structure as it rotated into view. The complex magnetic configuration made it a prime candidate for powerful eruptions, and the warnings proved accurate. Flares followed, radio blackouts spread across continents, and coronal mass ejections raced toward our planet once more. This is what solar maximum looks like in our time. This is the sun at its most active, following patterns that are ancient beyond measure, indifferent to the fact that we are watching, indifferent to the civilization we have built in the narrow space between its light and the darkness beyond. The current solar maximum has not been catastrophic. Power grids have remained operational, satellites have been protected, the precautions implemented after past storms have worked as designed. Some observers have breathed sighs of relief, interpreting the limited damage as evidence that we have the threat under control, but this interpretation requires caution. The May 2024 storm was powerful, even historic by recent standards, but it was not a Carrington-class event. We have not yet faced a truly extreme storm in the modern era, and the Sun is capable of far more than we have witnessed. Solar Cycle 25 has revealed how much remains uncertain about our star. The predictions failed significantly. The mechanisms that determine whether a cycle will be strong or weak remain poorly understood. We cannot reliably predict how intense activity will become or when the most dangerous events will occur. What we do know is that the Sun has reached its maximum phase, that activity is expected to remain elevated for some time yet, and that somewhere on its surface, magnetic field lines are twisting and building energy right now, preparing for the next eruption. The Sun continues its ancient rhythm, rising and falling in cycles older than human memory, older than human existence, and we, living beneath its light, can only watch and wonder and prepare as best we can for what might come next. If you're still listening, that's perfectly alright. And if you've drifted away and come back, that's alright too. The Sun will be here tomorrow, and the day after that, and the day after that, rising and setting in its ancient pattern, indifferent to whether we're paying attention or not. To understand what the Sun can do to us, we must understand how it reaches across that vast distance of space. The violence begins deep within the Sun, in the churning convective zone where superheated plasma rises and falls in constant motion. This movement, combined with the Sun's rotation, generates powerful electric currents that produce the solar magnetic field. But the Sun does not rotate like a solid ball. The equator spins faster than the poles, and this differential rotation stretches and twists the magnetic field lines over time, winding them tighter and tighter, building tension that must eventually be released. When magnetic field lines become too twisted, they reconnect in different configurations, releasing enormous amounts of stored energy in a fraction of a second. This process, called magnetic reconnection, is the engine that drives solar flares and coronal mass ejections. In an instant, energy equivalent to millions of nuclear bombs is released. X-rays and ultraviolet radiation blast outward at the speed of light, reaching Earth in just 8 minutes. Behind them comes something slower but potentially more dangerous, a billion-ton cloud of charged particles and magnetic fields, a coronal mass ejection racing through space at millions of miles per hour. When this cloud reaches Earth, if it reaches Earth, it collides with our magnetosphere. The magnetic field is compressed on the side facing the Sun and stretched into a long tail on the night side. Particles that would normally be deflected can penetrate deeper into the magnetic field. Electric currents flow through the ionosphere, the upper layers of our atmosphere, and these currents induce secondary currents in any conductor on the ground. Power lines, pipelines, telecommunications cables, anything metal that stretches across long distances. This is how the Sun can turn off our lights. This is how a flash of light 93 million miles away can, 18 hours later, plunge 6 million people into darkness. The long conductors of our electrical grids act like antennas, collecting the induced currents, channeling them into transformers and switching equipment. High-voltage transformers, the backbone of modern power systems, are particularly vulnerable. They can overheat, they can fail, and they take months or even years to replace because they are custom-built, enormous, and expensive. The question that haunts space weather scientists is not whether a Carrington-class event will happen again. The question is when. Scientists estimate there may be a 10 to 12% chance of such an event occurring within any given decade. Over a century, the odds become uncomfortably high, and our civilization is far more vulnerable now than it was in 1859, when telegraph wires were the only technology at risk. Today, we have built a world that depends utterly on electricity. Our food systems require refrigeration and electric pumps to move water through treatment plants. Our communication systems, from cell phones to the internet, require constant power. Our financial systems process transactions electronically. Our hospitals depend on electrically powered equipment. A prolonged, widespread blackout would not simply be inconvenient. It would cascade through every system we depend on, and the recovery could take months or years. But predictions of catastrophe require the same caution as predictions of safety. We do not know exactly what would happen during an extreme solar storm because we have not experienced one in the modern era. The May 2024 storm was powerful, but it was not Carrington level, and our systems handled it. Improvements have been made, monitoring has improved, forecasting has improved, protective measures have been implemented. The grid managers who work through the night when storms arrive are better prepared than they were in 1989, better equipped to respond, better able to prevent cascading failures. We are learning, we are watching. We are doing what humans do when faced with forces beyond our control. We are adapting, preparing, building resilience into systems that were not designed with space weather in mind. It may not be enough. It may never be enough. The sun is capable of events more powerful than anything we have witnessed in the modern era. But it is something, and something is better than nothing. There is a strange comfort in the sun's indifference. It does not hate us or love us or even know we exist. It simply follows the laws of physics, converting hydrogen to helium, releasing energy, generating magnetic fields that twist and reconnect according to processes that were operating long before Earth existed. We are not the target of its violence. We simply happen to be nearby, living on a small planet in what we hope is a safe distance from a star that owes us nothing. Every human who has ever lived has lived beneath this sun. Every story ever told has been told under its light. Every triumph and tragedy, every moment of joy and sorrow, every birth and death has occurred while the sun burned through 400 million tons of hydrogen every second, entirely indifferent to our existence. And we have built our civilizations on the assumption that this indifference will continue, that the sun will keep behaving in ways we can predict and plan for. Most of the time, that assumption holds. The sun is remarkably stable for a star of its type. It has been burning steadily for 4.5 billion years. It will continue burning for another 5 billion years or so, before it exhausts its hydrogen fuel and enters the red giant phase that will eventually consume the inner planets. We live during a stable period of a stable star, and for that we should be grateful. But stability does not mean perfect calm. Even a stable star has its storms, its moments of violence, its outbursts of energy that ripple across the solar system, and we, having built a technological civilization in the space of just a few centuries, must now learn to live with the reality that our technology is vulnerable to forces we barely understand. The sun will rise tomorrow. It will rise the day after that. It will continue rising for longer than we can truly comprehend. The dark spots will appear and disappear, following their 11-year rhythm. The magnetic field will twist and reconnect. Flares will erupt. Coronal mass ejections will race outward into space. Sometimes they will miss us. Sometimes they will strike us. And we will adapt. Or we will not. And the sun will continue either way, burning hydrogen, releasing light, following the ancient patterns that govern stars. There is a peculiar peace in accepting how small we are, how dependent on forces beyond our control, how fortunate to exist at all in a universe that makes no promises. We did not choose to be born beneath this particular star. We did not earn its light or its warmth. But here we are nonetheless, watching, wondering, trying to understand the mechanisms that make both life and destruction possible. The sun does not care. The sun cannot care. But we can care about each other, about the civilization we have built together, about the preparations we make and the resilience we cultivate. We can watch the dark spots rotating across the solar disk and remember that we are seeing something ancient and ongoing. We can see the auroras dancing across polar skies and remember that we are witnessing the magnetosphere at work, that invisible shield still protecting us as it has protected all life on Earth for billions of years. And if you've drifted off by now, that's as it should be. The sun will still be there when you wake. The story will continue whether we're listening or not. Rest well beneath the light of our indifferent star.